chapters 10 and 11, trigonometric functions and graphs. And we're going to go through this rather quickly, and we're not going to cover everything that was in these chapters. There was quite a bit in these chapters. So you might have to go back and review your notes or come back and watch this video again in order to get everything. But we have gone through this before, so again, check your notes if you need to help you on the study guide. And the study guide solutions will also be posted as well. Anyway, let's take a look at some of the things that we can remember from chapters 10 and 11. Given sides of a right triangle and an angle, we can find the missing information using our SOHCAHTOA, okay? And also from Pythagorean theorem, a squared plus b squared equals c squared. Well, if I ask something like this, I can find x because I know that x is going to be my adjacent to my angle, and 10 is the hypotenuse. So adjacent over hypotenuse, that would be the cosine value. So cosine of 38 equals x over 10. Using my calculator, I can figure out that that equals approximately 7.88. So you might want to try these on your calculator to make sure that you get the same answers. And if I had done it this way, if I had known that this was 7.88 and this was 10, I could use the inverse cosine. The inverse cosine of adjacent over hypotenuse will give me back the angle. So remember, a trigonometric function takes an angle as input and gives you a ratio. The inverse trigonometric function takes the ratio and gives you the angle. So these are inverse functions of each other. All right, well, let's take a look at a real-life application. The pilot of a small plane is flying at an altitude of 2,000 feet. The pilot plans to start the final descent towards a runway, which is when the horizontal distance between the plane and the runway is 2 miles. Draw a sketch of the pathway of the plane's descent, and then find the angle of depression theta from the plane to the runway at this point. Round your answer to 3 decimal places. All right, well, let's draw a picture of this so we can kind of understand it. So here is the airplane. Here is the runway where he wants to land. And we're told that he's at an elevation or an altitude of 2,000 feet. And we're told that he's 2 miles from the runway. Well, 2 miles times 5280 feet per mile, okay, is 10,560 feet, because we have to have the same units. Now we want to find this angle theta, which is also going to be this angle theta, because remember from our geometry days, alternate interior angles. So theta is going to be tangent of theta would be opposite over adjacent. So inverse tangent of opposite over adjacent will give me theta, and we find out that theta is approximately 10.724 degrees. All right, this one's a little bit tricky. It says solve for theta. Sine of theta is equal to 0.3, but we're going to be in quadrant 2. We're between 90 degrees and 180 degrees. 180 degrees. Now, so theta is going to be equal to the inverse sine of 0.3. 0.3 is my ratio, but my angle is going to be the inverse sine of that. But we have to remember that inverse sine, it's going to give me a value between negative 90 degrees and positive 90 degrees. So we have to then subtract our value from 180 to get us into quadrant 2. So if my inverse sine of 0.3 is going to give me 17.458 degrees, I need to subtract that from 180 to put me into quadrant 3. which is 162.542 degrees. So, so yes, that's between 90 and 180. And if I were to take sine of 162.542, it would give me approximately zero point 0.3. So yes, that checks out. So if I wanted to draw a picture of this, it would look something like this. Here's quadrant 1, here's quadrant 2, here's 90 degrees, here's 180 degrees. So my sine of zero point 0.3 would give me 17.458, but that would be in quadrant 1. We want the value in quadrant 2, which is going to have the same, same y value. So that's going to be here, and that's going to be the 180 minus 17.548. Okay? So if you need to come back to this slide, you can do that or take a screenshot. All right, angles of rotation. A sporting event runs from 1:25 p.m. to 3:45 p.m. Consider the rotation of the minute hand of a clock during that time. Draw a sketch of the angle of rotation indicating the initial side, terminal side, and rotational direction. Then find the measure of rotation generated by the minute hand in both degrees and radians. Okay, so if this is my clock face here, if I'm going to be going in clockwise direction, that's going to be a negative angle. And at 1:25, I'm just going to show the minute hand here. I'm not going to show the hour hand. So it would be here. That would be my initial side. Okay? Now, it's going to go to 3:45 p.m. Well, 45 minutes would be here. But now I have to go around, not from here to here. I have to go around from 1:25 to 2:25 to 3:25 and then to 3:45. So my squiggly little arrow there shows you the entire rotation. So the measure of rotation in degrees would be theta, okay, equals, I start at, this would be negative 30, this would be negative 90, and each turn around would be negative 360. So negative 30 minus 90 minus 360 minus 360 equals negative 840 degrees. Now, I didn't do it in radians, but you could convert negative 840 degrees to radians and solve that. All right, laws of sines. Remember we learned sine of A over A equals sine of B over B equals sine of C over C. Well, given the triangle ABC with sides A equals 8, B equals 11, and angle A equals 15 degrees, find side C. Well, we have, okay, what we have here is the ambiguous case of side-side angle. Okay, so we don't know if we have 0 triangles, 1 triangle, or 2 triangles. Okay, so let's take a look at what we've got. Okay, so I'm going to draw a picture here. So here's my side A. Angle A. Here's side A. Here's angle B. Here's side B. And here's, we don't know if for here, C is here or here. Okay, so my opposite side is going to be A, which is 8, which is going to be between the height and side B. So we're going to have 2 different triangles that we have to solve here. Okay? So let's use sine of B is to side B, which is 11, is to sine of 15, which is A, is to 8. So we can figure out what angle B is. angle B is going to equal inverse sine of 11 times sine of 15 over 8, and that would give us 20.847 degrees. Now, we also have to figure out what C is, and we can simply do that by 180 degrees minus A plus B, which would give us 144 degrees. The last thing we have to do is find side C. Okay, we can use the reciprocals of these here. So that would give us C is equal to 8 times sine of 144.153 divided by sine of 15, you kind of got cut off there, equals 18.101. So that's the first case. That would be out here, okay? The large triangle, okay? Now we're going to do this smaller triangle as well. So B prime, we'll call it. B prime is 180 degrees minus my original B, which would give me 159.153 degrees. So that's this angle here. Now I'm going to do the same thing to find C, subtract it from C prime, which is 180 minus A plus B prime, gives me a tiny little angle of 5.847, which is okay. Little c prime, we're going to use the same formula, except now we're going to use this smaller angle. And what do we come up with? We come up with little c prime is equal to, again, the sine of 15 degrees got cut off at the bottom there, is equal to 3.149. Okay. And with all of these triangles, it's a good thing to check. The largest side is across from the largest angle, and the smallest side is across from the smallest angle. So we've got two different cases here, and we should check that, and we would find that that is indeed true. So I know that's a lot of notes, and you might have to come back and grab these, but I don't want to take too much of your time right now. So you can come back and look at this. All right, so the last thing here would be the C and C prime. 18.101 would be the large side. 3.149 would be this small side, C prime. All right, we also looked at the law of cosines with these formulas up here. If we have side, 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 or side, angle, side. So solve the triangle ABC with A is equal to 69 degrees, B is equal to 34, C is equal to 46. Well, let's draw a picture of that. And we could draw it any way we wanted to, as long as side A is across from angle A, side C is across from angle C, side B is across from angle B. But what do we have here? We have B, A, angle A, and C. So we have side, angle, side. So we can use law of cosines, and this is the one we're going to use, the top one. A squared is equal to 34 squared plus 46 squared minus 2 times 34 times 46 times cosine of 69 degrees. If I plug that into my calculator correctly, I should get A is equal to 46.379 degrees. I'm sorry, 46.379 is the length of A. And we could then use this law of sines to find angle B using the information that we have. And we could figure out that side angle B is equal to the inverse sine of all this, which is equal to 43.188 degrees. We could then find angle C by subtracting those two from 180, gives us 67.812. So we know what A is, we know what side A is, we know angle B, we know side B, we know angle C, side C. And A is the largest angle, side A is the largest side by just a little bit, and B is the smallest angle and smallest side. So again, you can come back to this or take a screenshot if you need to. All right, let's take a look at an application problem here. A vertical pole, 36 feet tall, stands on a hillside that makes an angle of 14 degrees with horizontal. Determine the approximate length of cable that would be needed to reach from the top of the pole to a point 79 feet downhill from the base of the pole and rounded to 2 decimal places. So let's draw a sketch of this, putting all the different pieces together. The pole is 36 feet tall. The angle that the hill makes is 14 degrees. The top, the here's the pole is 79 feet from the base to where it's going to be anchored in. Okay, so here is the length of cable that would be needed. Well, if this is 14 degrees, then well, this angle would be 90 degrees, and this angle would be 180 minus 90 minus 1 minus 14. So this angle A we could calculate would be 14 plus 90 and would give us 104 degrees. Now that we know that, then we can use our law of cosines. And what do we have? 36 squared plus 79 squared minus 2 times 36 times 79 times cosine of 104. And A is equal to 94.41 feet. So A is the largest angle, side A is the longest, so makes sense. All right, we'll continue on. Area of a triangle. Okay. If I have area equal to 1/2 sine of the angle in between those two sides. Okay. And if we have side, then we can use Heron's formula using this semi-perimeter, which is half the perimeter. So we'll use this first one here. Area is equal to 1/2 3 times 2 times sine of 141. And if we plug that into our calculator, we should come up with 1.888 square centimeters. All right, let's find the area of this guy here. So the semi-perimeter is 1/2 8 plus 9 plus 10, which is going to be 13.5. The area then is going to be 13.5 times 13.5 minus 8, 13.5 minus 9, 13.5 minus 10. If I plug that into my calculator, and we take the square root of all that, come up with 34.197 square meters. Again, sorry for all the notes here, but a lot of stuff in this chapter. All right. The final couple slides, we don't have as many notes to take. So, sine and cosine graphs. Okay. Features of the sine and cosine graph. Remember, we had the wave function like this, and the sine function starts at the base, goes up to a max, comes back to the base, goes down to the min, comes back to the base. That is one period. Okay, that for a sine function and cosine function, that's going to be 2 pi. And here's where we've got the x-intercepts. Okay, the y-intercept for sine is at the base, that's 0. Cosine starts at a max, comes down to the base, goes down to the min, comes back to the base, goes back up to the max. So its a y-intercept is at 1, and then it's going to cross the x-axis at each pi over 2, 3 pi over 2, oops, sorry, 5 pi over 2. All right, and then we looked at how to change the amplitude of this thing and all kinds of things. So you might need to go back and check your notes for how to modify this function. But these are the base sine and cosine waves. All right, so the standard form, where A is the absolute value of the amplitude, okay? If A is negative, it's going to be flipped across the x-axis. Okay, the period is 2 pi divided by absolute value of b. As b increases, the period decreases. Okay, and you need those 5 key points, okay, that we saw to graph one period, and then once you have one period, you have the entire graph. So you might need to come back and look at this slide to remember how to graph these. Go back and look at your notes. All right, general equation with translation reflection. Okay, remember we had shift in the horizontal was h, shift in the vertical was k. Okay. Stretching and squeezing, okay, with a and b. Okay. So you might have to go back and review your notes on that. Okay, we did a whole packet on that back in this chapter. Okay, so you might need to go back and look at that packet of graphs that we did. Okay, so H, okay, shift to phase, right and left. K is a vertical shift up and down. Okay. Y is our baseline, right? If y is equal to 0, that's going to be our baseline. If we shift up with k, then we're going to have a new baseline. Tangent graphs were a little tricky. Okay. Domain is all real numbers except where cosine is equal to 0. Why? Because tangent is sine over cosine. So if cosine is equal to 0, then that's one of these asymptotes here. Okay. Okay, the period is pi, so it's going to repeat itself every pi. If you're going to do these on your calculator, you might want to put this x scale in terms of pi rather than in terms of integers like this, because pi would be here at 3.14, and pi over 2 would be right here at this asymptote. Right? So your asymptotes are right here. Right? All right, you might have to go back and review this section in your notes. All right, characteristics of graphing tangent. Okay, the period instead of 2 pi is now just pi divided by absolute value of b, and the asymptotes are pi over 2 times absolute value of b plus or minus pi over b and any n times that. So and there's going to be an infinite number of asymptotes for the tangent function. Okay. And that's where we're going to end. So I know there was a lot of stuff in there. You might have to go back and review your notes, uh, but please do. And if you have any questions, make sure you ask. So that's where we're going to end for today.